that was a dehydration of that alcohol. Dehydration to make the alkene. How about anything else? What else could have happened there? Was there another product that you predicted?
I reckon that was an E2.
E2?
Yeah.
E2 requires a strong base.
Yeah.
Sulfuric acid is not a strong base. Right?
True.
Sulfuric acid is a strong acid. E2 requires a strong nucleophile. SN2 requires strong nucleophile, E2 requires strong base. Bimolecular reactions require a strong nucleophile, strong base.
I have another question.
There was a question back here first, though. John?
Whenever you see heat, can you go ahead and apply the elimination?
Do what?
Whenever we see heat involved, can we assume that elimination is going to occur?
Not necessarily. No, heat favors elimination, but it's very general. I mean, you could heat one reaction at 100 and one reaction at 200. Which one's going to favor elimination more? 200. At 100, you might get substitution. That's heat. It's just more heat will favor elimination. I mean, a lot of substitution reactions require heat. But still, we can say heat does favor elimination because maybe at 100 you get substitution, but you do it at 200, then you get elimination. See what I'm saying? It's not an absolute thing. You can't just say any heat gives us elimination. More heat, more favored elimination. Over here.
Yeah, number 8 on page 27.
Number 8 on 27. Show two different substitution reactions that would give Prozac in good yield from smaller compounds. What do you need to do a substitution reaction? And when I say substitution, right now, how many substitution mechanisms do you know? SN1, SN2. At the end of organic 2, you will know numerous substitution mechanisms. Right now, you only know 2. Of the 2 you know, what do you need? Both of them require what? A nucleophile. Check. What else do they require? A tetraethyl carbon with a leaving group. Right? And these are the components of a substitution reaction. You're asked to show substitution reactions. What are the general components? Let's see. So we're making bonds here. Replacing something. Making bonds. Nucleophile, we're making a bond to a carbon in place of a leaving group. Which atom in this molecule, Prozac, could you envision being a nucleophile?
sp3 nitrogen.
This nitrogen?
Yeah.
Yeah, nitrogen is a good nucleophile. Okay, if the nitrogen was a nucleophile, that means it's going to bond to a carbon and kick off a leaving group. Is it going to bond to that carbon or this one? Which one do you want it to bond to? That one? So you want to make that bond right there. That's very reasonable. What would be the two components? You would break that down into, well, you'd have the NH methyl. There's got to be something else there. There's a lone pair there. And then you got to have all this here. I'll just cut it off there. Boom, boom. Okay. This nitrogen is going to have to bond to that carbon. Everybody agree? But we just can't have, I mean, what is this? Is this a CH3? What is this? I mean, that only has 2 bonds. That nitrogen, what needs to be here? What needs to be on this carbon?
Iodine. Good leaving.
Why not just CH3?
It's not leaving.
You need a leaving group. Something the nitrogen can replace. What's your favorite leaving group, babe?
Iodine.
Okay, iodine. Now what is going to be here? This is just, that's unreasonable. Week 1, so we have big problems there. What needs to be here? Charge? What kind of charge if you want it to be a charge? Karen? Minus? Well, if it's going to be a minus, there's got to be something else here in this to make it a complete structure. What else is needed?
Another lone pair.
Another lone pair. Then it would be minus. Okay, now step back. Can you envision this reacting with this to give that? What would be the mechanism? These electrons here kicking that off? Would that give that there? What would be the mechanism we just did? SN2. There you go, there's an SN2 reaction. What's the nucleophile? That, what did it replace? You got to envision replacing a leaving group with something new. Now, did we have to use the anion here? No, we could have used the neutral amine. Why? Because a neutral nitrogen, sp3 nitrogen, is also a strong nucleophile. And if you had used this, we would have gotten this with an H here. We would have had to include a base to get rid of the H. Either way works. They both would be SN2 reactions. Okay, what's another bond we could have made? Who's this? How much?
Oxygen with the tunnel.
Here?
No.
In front.
The other one. The right.
Here.
Yeah.
Yeah, I like that side better. Because that's a tetrahedral carbon. So what do you want to have here?
The F3C with the benzene ring and the O, and just leave it there.
Make that minus. I'll just call that phenol. What do you want on this carbon? Something like this? And we can have this come in here and kick that off. That's what, an SN2? Can you do an SN2 on this carbon?
Yeah.
Uh-huh. Yeah, that would give that. SN2.
How would you do an SM1?
So the anion use the alcohol, the phenol. Just OH, CF3. Reacting with the same molecule. And probably heat. This would be phenol. Those two with heat. Keep that as a neutral. And because that's neutral, it's not going to do an SN2. You heat this thing, this will just ionize, make carbocation, then that'll add. And you'll be doing SN1 because you made carbocation and then the nucleophile added. If you keep this neutral, if you make it an anion, it's going to do SN2. Because now it's strong, strong, strong. But this would be a weak nucleophile. I don't see any benefit of doing SN1. It's going to be a more difficult reaction. You don't want to do over here because if you had an O minus, if you had a leaving group on that carbon, tough. You're not going to do any SN1 or SN2 there. We could have made that bond. We could have had the NH2 and like methyl iodide or something, CH3I. And the NH2 could have just attacked this and kicked off the I. I see three places to make bonds here. I mean, you could maybe envision making this bond, but that's going to require carbanion. Carbanions are hard to make. Very often your heteroatoms, oxygens and nitrogens and sulfurs, those are your nucleophiles. I mean, we did see examples of carbon as a carbanion. Are there other questions there? Karen?
The second one on 29.
Mechanism on page 29. We have this and HCl. What can we do first? Coordinate the oxygen. I'll tell you a little hint. Don't tell anybody I told you this. If you're under acidic conditions, usually the first thing you do in a mechanism is you protonate something. What do you want to protonate? Protonate the oxygen. And we have this here. What do you want to do now? We have Cl minus. This is a mechanism we see. We want the chlorine to bond to the benzylic carbon. We want the chlorine to bond to there. What do you want to do next? I see two things you can do here. You can ionize this off. This leaves, we get ethanol, which is we got to make. I also see this could attack here and kick that off. In both of those cases, we're going to form ethanol, which is made. Do you want this just to ionize off and make cation, or do you want this to attack here and kick it off?
Okay, how can it
Can't you-
ionize though? Because I thought we just said OH isn't a good leaving. Oh, it's not a good leaving.
No, an OH, this is not an OH. I mean, it's, how do you make OH a better leaving group? Okay, we should broaden that out. How do you make oxygen a better leaving group? You make it positive. How do we make it positive? You protonate it, now it's positive. See, this is positive here, but it'll be protonated. This is a we make this oxygen a better leaving group by making it positive. That oxygen's a good leaving group, it's positive. This can just ionize off. If it does, what does that give? It gives this cation plus, see now the oxygen gets its lone pair back. It leaves as a neutral species. And there's the ethanol right there. All right, now what do you want to have? A chlorine attack here? Well, that would not give that product. We got to get the chlorine bonded to this carbon. Hydride shift.
Why would the hydride shift happen there?
Well, that's a benzene ring. They're both secondary, but why is this one better? Resonance stabilized. We can draw resonance structures. It rearranges to a resonance stabilized secondary carbocation. Now what's the chlorine do? And what does that give? Why is it racemic?
SN1.
Because anytime you attack a carbocation, you attack it from either side. So there's your two products.
So since it said racemic on the answer, that we could take that as a clue in the mechanism that it will be the SN1 and not the SN2, which is chlorine attacking.
Right.
And the placement of the chlorine.
Yeah, but it has to be SN1. I mean, how is it SN2? There's no leaving group on that carbon. SN2 is always a direct displacement. You're never going to get rearrangement to the SN2. So seeing that the chlorine is on that carbon, which is this carbon, it's like there's no leaving group there. So that's also a clue. It had to be somehow a cation got there. SN2 is always a direct displacement of the leaving group. There's no leaving group there. That can't. The chlorine cannot get there by SN2. Question over here.
On the Elimination bracket, can you do the one that's on the bottom of what page?
Yeah, we did not. We didn't go over these. We need to go over these. Let me finish this up first. Which ones did we do? First two?
Yeah. So we have three. You did three.
Do what?
We did the top three.
We did this one with triethylamine.
Yeah.
We didn't do the bottom two though. Both of these look like a hydroxide base, leaving group, double bond, we're doing elimination. Because this is hydroxide, we're doing what type of elimination? We're doing E2. Which reaction would be faster? In both cases, we're taking H here, we're removing HI. HI, putting double bond in here. There are two H's here, by the way. A and B. Which H is being removed?
Alpha.
So,
The one that's trans to the leaving group or the one that's cis?
Trans.
Trans, because it would be transcoplanar or anticoplanar. The one that remaining, HB would remain. Which would be faster? What's the difference in these? The difference is here the T-butyl group is cis to the leaving group, here it's trans to the leaving group. Somebody have an idea which would be faster? What do we need? What do we know about the requirements of this reaction? The leaving group must be what? It must be axial. Why must it be axial?
so the beta hydrogen would be
Because only when this is axial will a beta hydrogen be anticoplanar. And when this is axial, HA will be anticoplanar. If you don't believe me, let's look at it. Let's put the iodine axial. Here's the next carbon with two H's. One of them is straight down and one of them is equatorial. Well, here, there's an H there, but we're not considering that one. That's not a beta hydrogen. Is this H here cis or trans to the iodine? Cis. So is it A or B?
B.
That's B. This is A. This is cis to the iodine. They're both up compared to the H's. This is trans to the iodine. It's down compared to the H. This is up compared to the H. This is trans. This is A. But also, you see how this is anticoplanar. That's straight up. This is straight down. Anticoplanar. The hydroxide takes the A, these move in, and that gets kicked off. Now, where's the T-butyl group at? It is not on that rich here. For this molecule, is the T-butyl axial or equatorial? Well, it's cis. Well, this is an up and an equatorial. If it's cis, what is this? I mean, the T-butyl is what? It's also here. Let's just get rid of that. Unless you want to keep it, there's an H there, right? Okay. Both of these big groups are axial. Let's draw this one down here. We're going to draw the same exact thing. What's that? A? And that's it. But over here, this is equatorial. So over here, these are trans. Right? But here they're cis. And this is A. And this is B over here. These are the conformations that the molecules have to exist in to eliminate with the iodine axial. Which reaction would be faster? The answer is the one that will exist in this conformation most readily or most likely. Which one is going to exist in this preferred, this needed conformation most likely? B. Why is this one going to exist like this more often?
What's the one?
Because the T-butyl is happy being equatorial. Is this molecule going to want to exist with both of these groups active? Hey, why not? This molecule is dying to do a ring flip, right? This molecule wants to do a ring flip and both become equatorial. Is that one over there dying as much to do a ring flip? No. So when this molecule is walking down the road, which one's more likely to exist like this? The one on the right. This molecule is going to exist like this. This is going to be equatorial, and this over here is going to be equatorial. It's going to prefer to be both equatorial. It's going to be really preferred. But then guess what? You can't eliminate. And since you can't eliminate, then the reaction is going to be slow. You got to wait for it to do this, but it's not going to be doing that much. What you're really trying to figure out here is which one is going to exist more often, more likely, with the leaving group being active. That's really what you're trying to figure out. Which one is it? That one? B? Yeah, this one. B will be faster. It turns out that the trans is going to be faster. Okay? Does that mean that if the T-butyl was here, the trans would be faster? No. So don't memorize that trans eliminates faster. Does that make sense? What other elimination product could be formed in reaction A? What other product could be formed? Somebody have it? Camille, you got it? You want?
Would the double bond be on top?
Put the double bond in up there. Yeah. Remove HI up here. Put in the double bond up there.
Is that unique to just A? You could do the same thing with D, right?
Is it what?
You could do the same thing in both of them.
Except
Right.
Yeah, you can also do it down here.
Okay.
Which is going to be favored? I don't know. They're going to be just as likely. See, here I gave you a product and asked you a question about that. But this alkene is almost just as likely to form. I see no reason. They're both di-substituted. I don't know why you would have any selectivity unless somebody sees something. Other questions? On the quiz, let's look at the quiz. Substitution was probably the most straightforward on the page. Replace the BR with a nucleophile with inversion, because it's SN2, it should be bold and bold with an OH. A number of people got that. A number of people showed a dashed OH. I mean, it's either going to be inversion or racemic. Strong nucleophile SN2, it should be inversion, so this should be bold as long as the background's the same, the backbone is the same. Elimination. You always prefer to have Sate-Sef. There's two reasons why you would not get Sate-Sef. And these are here. First reason you may not get Sate-Sef is the base is too bulky. The base is too bulky, you may get the Hoffman product. But is hydroxide a bulky base? No. So you don't have a bulky base. Another reason you may not get Sate-Sef is the H that you have to remove cannot be anticoplanar. Well, here it can be. You just have to find the right orientation. You're going to remove this H here and put the double bond in there by removing HBr. But to do this, are you going to get the product with ethyl there and methyl up top? Or are you going to get like this, which is going to be formed? The stereoisomers of the Sate-Sef product. Turns out that this one's going to be formed. The Z product. You have to draw this in a Newman and then rotate it. The H and the Br need to be anticoplanar. A number of people showed this Sate-Sef product, which showed E instead of Z. In the second one, I don't think anybody got this one right. Anybody get it right? I don't think so. And only a couple of people showed a sort of alternative product that was not actually right, but it's. What you have here is you got two OHs. A lot of people tried to have these be leaving groups. How do you make OH a better leaving group? Protonate it with what? A base or an acid?
Acid.
An acid, right? Okay. We protonate things with acids. Is that an acid? No, that's a base. Sodium hydroxide, base. Right? Of course. There's no acid there. There's no acid anywhere on number 2 problem. If there's no acid, these guys aren't going to be leaving. That's a base. What does a base do? Removes H's. Where's the most acidic H? What do? Well, if you're going to remove an H, you look for the most acidic one, right? Go back to week 2. That's what we say. Okay, where's the most acidic hydrogen in this molecule? You've got a base, it wants to remove an H, it's going to remove the most acidic. It's up to you to figure out which one. The molecule knows, but you need to know. Which one's most acidic? This one here on that carbon? No, it's one of the OHs, right? You want an O on a negative on oxygen, but which one? This one's most acidic. Why? Because the resulting anion will be resonance stabilized. Sodium hydroxide makes anion here. Boom. Number 1 is done. Now you throw in this and it is a carbon with a leaving group. Deuterium is not a leaving group. That's just an H with an extra neutron and we call it D. The chemistry is the same except we need to finish up the handout. Boom, boom, kick off this. Oxygen is now bonded to that carbon with inversion, SN2. I received answers where this oxygen or that oxygen was bonded to that carbon. I don't know how. Right? That's the carbon with the leaving group. Okay, the other one's mechanism needs lots of work. Stepwise, okay? What can you do here? Protonate oxygen, that's the only thing you know how to do. You can then I minus, okay, this is not HI, but essentially it is because that's proton and this is I minus. I can tack here and kick that off, but that won't give you that product. So it must be ionization. From there you can check the key. Let's finish up the handout because there's a couple of important things. Polar solvent. Makes sense? Polar solvent is going to favor ionization. Next, deuterium isotope effect. I think we introduced this. Is this E1 or E2? Two ways to tell. First, kinetic study. If it's E2, the base should be involved in the rate determining step, and the concentration of the base should just thus affect the rate. Repeat the reaction with double the concentration of base and see if the rate doubles. If it does, it must be E2. If it doesn't, it must be E1. So your rate equation is very important to know, understanding changes in that. Another way to do this is a deuterium isotope effect. You can read this here. I'm going to just basically tell you what this reads, okay? If you instead of the beta hydrogen, if you replace that hydrogen with the deuterium, which is what I've done here, in this reaction, this hydrogen is removed, HBr is removed to put in the double bond. Replace that H with the deuterium and then do the reaction again. And see if the rate changes. Now let me ask you a general question. In which mechanism, E1 or E2, is the beta hydrogen bond broken in the rate determining step? In which one is the beta hydrogen bond broken in the rate determining? E1 is just ionization. That's all the rate determining step is. E1 would be this ionizing to give that, right? That's the rate determining step of an E1, just like an SN1, ionization. Right? Did we break the bond? No. The next step is the base takes the H or D and puts in this, but that's fast. Right? But what if it was E2? The base would take that, this comes in all together. If this was E2, this bond is broken in the rate determining step because it's only one step. The beta hydrogen bond is broken in the E2 rate determining step, not the E1 rate determining step. Now, the deuterium carbon bond is stronger than the H carbon bond. Mass effect. And so, it's going to be more difficult to break the deuterium carbon bond because it's a stronger bond. If it's E1, does that matter? No, the rate determining step has nothing to do with breaking that bond, so it isn't going to matter. It may make the fast step a little slower, but that doesn't matter as long as it remains the fast step. But if it's E2, we're breaking this bond in the rate determining step, so this should be more difficult with the deuterium. So it's a rate study, but it's instead of changing concentration, we're changing the H to a deuterium. So it's a isotope study, or you're looking for an isotope effect. In summary, the deuterium carbon bond is harder to break. But that only would matter if it's E2. And that's what this says here. So, change the beta hydrogen to deuterium, see if that makes the reaction slower. If it does, it must be E2. Finish up this, then I want to look at the deuterium on the back. Anybody have these real quick? What are we doing here? Substitution elimination. We're not going to be able to look at the one on the back. The very back is a deuterium example where it's a drug being metabolized, and drug companies are replacing H's with deuterium to slow down that metabolism. You can take a look at that. It's good for pharmacology, drug design. Let's look at this, substitution elimination. Show the substitution product here. Somebody got these? SN1 or SN2?
Two.
That look like an SN2? Hydroxide your nucleophile. This must just be solvent, isopropanol. SN2. Elimination, E1 or E2? Strong base, E2. Let's see, leaving group. There's an H here. It's like this. There's also H's there. A, B, C, and then that's D. What's the product here?
Can the base take that deuterium?
Do what?
Can the OH minus take deuterium?
Right, just like it did here? Yes, it can.
It can?
But is it going to want to?
No.
No.
Of A, B, C, or D, which one is it going to take?
E.
D?
E.
B? Very good. B. Product here will be HA, D, HC, yes, E2. Why did it take HB? Because it's going to be transcoplanar. Well, so with the deuterium. Which is going to be preferred, that H or that D? H, because it's a weaker bond. Now, if there was nothing up here, it could take the D. It'd be a more difficult reaction, but D can be. But if you have a choice between H or D and they're both the same, they both meet the stereochemical requirement, you'd rather take the H. It's going to be a weaker bond, thus an easier reaction to do. Ethanol, what's the silver for? I'll let you do this one at SI. SI today at 3 o'clock, yeah? I sent an email? Oh yeah, tomorrow. Tomorrow at 3. Same time as usual. Is that 3? Yeah, just a day earlier this week. If the room is used, we'll have to find another room. SI tomorrow at 3. Of course, you can do a double E2 elimination down there. Take a look at that. The final exam, the test on Wednesday is similar format. We got nomenclature. We have resonance. We have mass spec. We have dyeing chemistry. Substitution elimination. Anything else? Well, there may be an IR included with the mass spec, like in the workbook. Yeah. Anything else? Anything else about the test on Wednesday? If you have any questions, let me know.
I guess not.
The key for the last quiz is posted. See you then, guys.
I don't think
Dr. Steven, do you want our lab?
Yes, thank you. You're turning your lab on the way out. Lab. We do, day of the week, please. Friday by the computer. What day? Thursday over here, Friday by the computer. Thursday over here, Friday by the computer.